Picture a time when the universe was a vast, shadowy void, a cosmic canvas where the first sparks of light struggled to pierce through an ocean of darkness. This was the Cosmic Reionization Era, a chapter in our universe's story so mysterious, even the brightest minds in astrophysics are still piecing together its secrets. Think about it. Over 13 billion years ago, the cosmos transformed from a fog of neutral gas into the glittering expanse of stars and galaxies we see today. But how, what cosmic forces were at play, and why does this era hold so many unanswered questions? Today, we're diving into 25 of the most perplexing enigmas from this pivotal moment in time, a journey that will take us to the edge of understanding and beyond. The Cosmic Reionization Era wasn't just a transition, it was a revolution. For hundreds of millions of years after the Big Bang, the universe was a cold, murky place, filled with hydrogen atoms so dense they swallowed light whole. Then something extraordinary happened. The first stars flickered to life, their searing ultraviolet radiation tearing through the cosmic fog, stripping electrons from atoms in a process we call reionization. This wasn't just a flick of a switch, it was a slow, chaotic dance of light and matter that shaped everything that came after. Without it, galaxies as we know them might never have formed. The night sky could have remained forever dark, yet despite its importance, this era is riddled with gaps in our knowledge. What triggered reionization? Were the first stars alone responsible, or did something else, something even more exotic, play a role? That's where the mysteries begin. From the elusive nature of the universe's earliest galaxies to the baffling behavior of ancient quasars, the Cosmic Reionization Era is a treasure trove of cosmic riddles. Some questions are so profound they challenge the very foundations of physics. Others hint at forces and phenomena we've yet to discover. And as we peel back the layers of time, each clue we uncover only deepens the intrigue. So, if you've ever looked up at the stars and wondered how it all began, you're about to embark on an adventure that will change the way you see the cosmos. Because this isn't just a story about the past, it's a key to understanding the universe's future and our place within it, ready to explore the unknown. Let's begin. The first mystery pulls us straight into the heart of the cosmic unknown. What exactly flipped the universe's great switch from darkness to light? For centuries, scientists assumed the answer lay with the first stars, those colossal behemoths hundreds of times more massive than our sun. Their blistering radiation, we thought, acted like a cosmic blowtorch, burning away the fog of neutral hydrogen that had shrouded the early universe. But as telescopes peer deeper into time, that story's grown far more complicated. Some galaxies from this era appear to be reionizing their surroundings at rates that defy expectations, while others seem oddly quiet, as if something else, something invisible, is doing the heavy lifting. That's where the theories collide. Could quasars, those ravenous supermassive black holes blazing with energy, have supercharged reionization? Their jets stretch across billions of light years, pumping out enough ultraviolet radiation to strip entire galaxies bare. Yet there's a problem. Quasars were vanishingly rare in the early cosmos. If they were the primary drivers, why does reionization appear so uniform across the sky? Others point to dark matter, the universe's ghostly scaffolding. What if unseen particles decaying or colliding in the cosmic dark released enough energy to ionize the universe from within? It's a tantalizing idea, but one that dances on the edge of what our current models can explain. The truth might be messier still. Perhaps it wasn't one trigger but a chaotic symphony of sources, stars, quasars, and even the tumultuous birth cries of the earliest galaxies all playing their part. Every new observation seems to add another layer of intrigue. Take the recent discovery of ancient galaxies glowing with unexpected intensity in far ultraviolet light. These cosmic overachievers might have punched above their weight, ionizing vast regions of space long before theory predicted they could. Then there's the puzzle of timing. Reionization didn't happen everywhere at once. Patches of the universe flickered awake like city lights on a rolling blackout, leaving astronomers to wonder what dictated which regions woke first. This isn't just academic curiosity. The trigger of reionization shaped the blueprint of the cosmos. Without it, galaxies might have remained small and isolated, their gas forever trapped in neutral darkness. The very existence of spiral arms, superclusters, and perhaps even planets like Earth could trace back to this pivotal moment. Yet after decades of research, the definitive answer still floats just beyond our grasp, hidden in the faint whispers of light from the edge of time. Each theory weaves part of the story, but the full picture, that remains one of astrophysics' greatest unfinished puzzles. The next puzzle takes us deeper into the fog of cosmic time. When exactly did the universe flip the lights on? Pinpointing the timeline of reionization is like trying to read a stopwatch buried under 13 billion years of stardust. Some clues come from the cosmic microwave background, that faint afterglow of the Big Bang. Tiny distortions in this ancient light suggest reionization was well underway by the time the universe hit its 500 millionth birthday. But here's where things get strange. Glimpse even further back using the light from distant quasars, and you'll find patches of space still swaddled in neutral hydrogen long after that, as if the cosmos couldn't make up its mind. These conflicting signals have astronomers scratching their heads. Imagine two clocks from the same event. One says it happened at noon, the other insists it was twilight. That's the kind of discrepancy we're dealing with. The cosmic microwave background paints a picture of a relatively quick process, wrapping up by the time the universe turned 1 billion years old. Yet quasars tell a different story, revealing pockets of neutral gas lingering stubbornly in place, like shadows refusing to fade. Could reionization have been a stop-and-start affair, flickering across the cosmos in fits and bursts? Or are we missing something fundamental about how these ancient light sources interacted with their environment? This isn't just a debate over dates. The timing of reionization holds the keys to understanding how structure emerged in the early universe. If it happened earlier than we think, it might mean the first galaxies were monstrously efficient at churning out ionizing radiation. A later timeline, though, could hint at unseen players, perhaps exotic particles or even primordial black holes stirring the cosmic pot. And then there's the wrench in the works. Recent observations of galaxies born just 200 million years after the Big Bang, already pumping out enough radiation to challenge every textbook model. How could these fledgling firebrands have existed so soon, in a universe supposedly still cloaked in darkness? That's why all eyes are on telescopes like the James Webb Space Telescope. With its infrared vision, it's peeling back layers of time we've never seen before, hunting for the faintest glimmers of the earliest stars and galaxies. Every new observation could rewrite the timeline, narrowing that tantalizing window when darkness gave way to light. Until then, the mystery of timing remains a cosmic tug of war between evidence and theory, a reminder that even our best tools are still just scratching the surface of the universe's deepest secrets. And as we wrestle with these questions, another thought lingers. What if reionization wasn't a single event at all? What if it was more like a symphony, with different sections of the universe awakening to light on their own schedule? The implications would ripple across cosmology, forcing us to rethink not just when the lights came on, but how the universe orchestrated its own transformation from the void. Now picture the early universe not as a uniform sea of light, but as a cosmic patchwork, bright islands blazing amid vast stretches of lingering darkness. This unevenness, called the patchiness of reionization, is one of the era's most baffling features. If reionization was driven by the first stars and galaxies, why didn't their light spread smoothly, like dawn breaking over a calm ocean? Instead, simulations reveal a chaotic mosaic with ionized bubbles expanding at different rates, colliding, and sometimes even leaving behind isolated pockets of neutral hydrogen like twilight holdouts. The clues lie in the distribution of those first light sources. Imagine tossing a handful of glowing pebbles into a pitch-black pond. The brightest ones create wide circles of rippling light, while dimmer ones barely pierce the gloom. That's essentially what happened in the early cosmos. Galaxies forming in dense regions where matter clustered like cosmic cities, pumped out enough radiation to carve massive ionized bubbles around themselves. Meanwhile, sparser regions remained shrouded, their gas untouched for hundreds of millions of years longer. But here's the twist: even among galaxies of similar size and brightness, some created enormous bubbles while others barely ionized their immediate surroundings. This inconsistency throws a wrench into our models. If early galaxies were the sole architects of reionization, their bubbles should correlate neatly with their size and power. Yet observations suggest something else was at play, perhaps the unpredictable ways radiation escaped galactic nurseries. Young stars often form deep within thick clouds of gas, their light stifled like a flashlight wrapped in layers of cloth. Only when stellar winds or supernovas blasted open pathways could that radiation flood outward. Some galaxies might have cleared their throats early, while others simmered in isolation, delaying their contribution to the cosmic dawn. Then there's the dark matter factor. The invisible scaffolding of the universe dictated where galaxies could form, creating uneven clusters of potential ionizing sources. But dark matter's distribution wasn't perfectly smooth either. It had its own subtle ripples and voids. These imperfections could explain why certain patches of the universe remained stubbornly neutral long after their neighbors had lit up. Even stranger, some simulations hint that early magnetic fields or turbulence in the cosmic gas might have played referee, either helping or hindering the spread of ionization in ways we're only beginning to grasp. The implications are profound. If reionization was this patchy, it means the universe's transition to light wasn't just a single event but a sprawling, fragmented revolution. Some regions became galactic hotspots early on, forging ahead in the race to complexity, while others languished in the dark, their gas too pristine to collapse into stars. This uneven start might have set the stage for the cosmic diversity we see today: superclusters blazing with galaxies alongside desolate voids where matter never quite got its act together. And as telescopes peer deeper into this era, each new map of the bubbles only deepens the mystery, reminding us that even the universe's most pivotal moments were messier and far more fascinating than we ever imagined. Imagine stars so colossal they make our sun look like a speck of dust stars forged from the universe's rawest ingredients, blazing with intensities we can barely fathom. These were population 3 stars, the universe's firstborn, and their role in reionization might be the most tantalizing cosmic what-if of all. Born from clouds of pure hydrogen and helium, untouched by heavier elements, they burned at temperatures dwarfing modern stars, unleashing torrents of ultraviolet radiation that could rip electrons from atoms across vast distances. Their brilliance was their downfall, though these titans lived fast and died young, exploding in supernovas so violent they seeded the cosmos with the first traces of elements like carbon and oxygen. Yet despite their monumental impact, we've never directly seen one. The hunt for population 3 stars is like searching for ghostly footprints in the cosmic sand. Their ephemeral existence, some lasting just a few million years, means even our most powerful telescopes struggle to catch their flicker at the edge of observable time. But indirect clues abound. Take the peculiar chemical fingerprints of ancient quasars and galaxies, traces of heavier elements where there shouldn't be any, hinting at the ashes of long-dead giants. Or the bizarre shadows cast by the cosmic microwave background, where patches of the early universe appear ionized earlier and more aggressively than standard models predict, something only stars hundreds of times more massive than the Sun could explain. Then there's the supernova puzzle. When population 3 stars finally met their end, they didn't fade quietly. Their deaths were cosmic fireworks shows, detonating as pair instability supernova, a rare, catastrophic event where the core collapses under its own gamma rays, annihilating the star entirely. These explosions didn't just light up the early universe, they turbocharged reionization, blasting heavy elements into the void and paving the way for the next generation of smaller, longer-lived stars. Some theories even suggest these supernovae created the universe's first black holes, seeding the growth of the supermassive monsters we see at the hearts of galaxies today. Yet for all their theorized influence, population 3 stars remain just that, theories. The James Webb Space Telescope might finally change that by scanning the infrared sky for the unique light signatures of helium-dominated stars or the telltale aftermath of their supernova. It could snap the first cosmic family photo of these elusive pioneers. Until then, their legacy is written in the stars around us, in the chemistry of our own bodies, forged in the hearts of those primordial giants. If reionization was the universe's awakening, population 3 stars were the match that lit the fire. And somewhere, in the faintest glimmers of 13-billion-year-old light, their story is still waiting to be told. Quasars should have been the universe's ultimate reionization powerhouses, lighthouses in the cosmic dark with beams so intense they could strip electrons from atoms across billions of light years. Yet when astronomers tally up the known quasars from the early universe, the math doesn't add up. These brilliant beacons, it turns out, are vanishingly rare in the Cosmic Reionization Era. For every quasar we've spotted, there's a glaring gap in the ionization they should have produced, leaving scientists to wonder, where's the missing energy? One possibility is that we're simply not seeing the full picture. Quasars are the ravenous cores of galaxies, powered by supermassive black holes gorging on gas. But what if the early universe hosted a hidden population of smaller, dimmer quasars, ones too faint for our telescopes to detect? Think of it like trying to count campfires in a foggy valley from a mountaintop. You'll spot the bonfires easily, but the smaller flames, they might slip through unnoticed. Recent simulations suggest these overlooked quasars could outnumber their brighter cousins 10 to 1, their collective radiation quietly ionizing vast swaths of the cosmos. But without direct evidence, they remain ghosts in the equations. Then there's the faint galaxy theory. While quasars steal the spotlight, humble dwarf galaxies might have done the heavy lifting. These cosmic underdogs, barely a fraction the size of the Milky Way, could have packed a surprising punch. Their stars, though fewer in number, were hotter and more violent than modern ones, spewing ultraviolet radiation like sprinklers in a desert. Multiply that by millions of undiscovered dwarfs lurking in the shadows of the early universe, and suddenly the energy budget starts to balance. The James Webb Space Telescope has already spotted galaxies in this era glowing with unexpected intensity, their light signatures hinting at frenzied star formation. Could armies of these tiny but prolific galaxies have outshone quasars where it mattered most? But the plot thickens. Some regions of the early universe appear over-ionized like patches of a forest burned too thoroughly for the known arsonists to blame. This has led to wilder theories, decaying dark matter particles releasing energy as they vanished, or even primordial black holes, born in the chaos of the Big Bang, evaporating in bursts of radiation. These exotic explanations linger on the fringe of physics, but they underscore how perplexing the missing quasar problem truly is. The stakes are higher than they seem. If quasars weren't the primary drivers of reionization, our understanding of how black holes and galaxies co-evolved needs rewriting. And if faint galaxies carried the torch, their descendants, those dim, diffuse dwarfs orbiting modern galaxies, might hold chemical fossils of their explosive youth. Every new observation chips away at the mystery, but for now, the missing energy remains one of the Cosmic Reionization Era's most tantalizing gaps, a reminder that sometimes the universe's quietest players might have shaped its brightest moments. Among the most cryptic clues from the Reionization Era lies in the ghostly fingerprints stamped across the light of distant quasars, a phenomenon astronomers call the Lyman-alpha forest. Picture a quasar's brilliant beam traveling billions of years through space, only to pass through clouds of hydrogen gas that act like cosmic sieves. Each cloud absorbs a specific slice of the quasar's light, leaving behind a barcode of dark lines in its spectrum. Normally, these lines should follow predictable patterns, reflecting the density and temperature of the gas they pass through. But in the Reionization Era, something's off. The lines cluster in ways that defy expectations, hinting at a universe caught in the throes of a turbulent transformation. What makes these anomalies so baffling is their inconsistency. Some regions show absorption lines packed tightly together, as if the gas there was clumped into dense knots. Others stretch thinly, suggesting vast ionized bubbles where the hydrogen has been stripped bare. It's like analyzing tree rings from an ancient forest and finding some years where the growth patterns zigzag wildly for no apparent reason. These fluctuations point to a reionization process far messier than we'd imagined, not a steady dawn, but a flickering strobe of ionization, with some areas blazing to life while others stubbornly clung to darkness. Part of the mystery lies in the culprits behind these fluctuations. Were they caused by the uneven distribution of early galaxies, some regions teeming with ionizing stars while others languished in isolation? Or did something more exotic, like the violent energy of collapsing gas clouds or the shockwaves from primordial supernova, punch holes in the hydrogen fog? Even the temperature of the gas plays a role. Simulations show that colder hydrogen absorbs light differently than warmer gas, creating spikes and dips in the Lyman-alpha forest that don't align with our models. It's as if the universe left us a puzzle where half the pieces are from a different box entirely. The most tantalizing clue comes from quasars at the very edge of observable time. Their Lyman-alpha forests often vanish entirely, swallowed by what astronomers call the Lyman-alpha dropout, a shadow so deep it suggests the gas around them hadn't just been ionized but utterly obliterated. Were these the work of quasars so powerful they blasted their surroundings clean? Or evidence of a brief, catastrophic phase in reionization where entire swaths of the universe were scoured of neutral hydrogen in cosmic eye blinks? The answers might rewrite our understanding of how light first conquered the cosmos. This isn't just about decoding ancient light. The Lyman-alpha forest anomalies are a time capsule from an era when the universe was still figuring itself out. Every irregularity, every unexpected gap or cluster is a snapshot of a moment when the rules of physics were being stress-tested in ways we're only beginning to grasp. And as telescopes like Webb and the upcoming extremely large telescope peer deeper into these spectral fingerprints, they're not just reading the past, they're uncovering the chaos that paved the way for everything that followed. Dark matter's invisible hand might have quietly shaped the cosmic reionization story in ways we're only beginning to unravel. While we often picture this mysterious substance as passive scaffolding, guiding galaxies together with its gravitational pull, some theories suggest it played a far more active role in the universe's Great Awakening. Imagine dark matter particles not just lurking in the shadows, but occasionally brushing against ordinary matter, leaving behind traces of energy like cosmic static. These rare interactions could have heated the early hydrogen fog, making it easier for the first starlight to tear electrons free and accelerate reionization in unexpected pockets of space. The wild card here is something called dark photons, hypothetical particles acting as messengers between dark and ordinary matter. If they exist, these shadowy carriers of force might have transferred energy during collisions, subtly warming the hydrogen gas that filled the early universe. Warmer gas is easier to ionize, meaning even a faint trickle of dark matter's influence could have given reionization a head start in certain regions. Simulations show this process creating a patchwork of slightly warmer and cooler hydrogen, matching the strange unevenness we see in the Lyman-alpha forest. But here's the catch: no one's ever detected a dark photon. The idea remains a tantalizing what if, hovering at the edge of physics' known laws. Then there's the decay theory. Some models propose that a fraction of dark matter might be unstable, slowly breaking down over billions of years and releasing energy as it vanishes. In the reionization era, this decay could have acted like a cosmic slow cooker, gently heating the universe from within. Unlike stars or quasars, this energy wouldn't come from discrete points, it'd seep uniformly through space, potentially explaining why some regions appear ionized earlier than our models predict. The challenge: we've yet to find any proof dark matter decays at all. Its stubborn persistence is one of its defining traits. Observational clues add another layer of intrigue. Certain dwarf galaxies' relics from the early universe show star formation patterns that don't align with standard dark matter predictions. Their gas seems to have been preheated somehow, as if an unseen force prepared it for ionization long before the first stars flickered to life. Could these anomalies be fossils of dark matter's subtle nudges during reionization? Or are we reading too much into cosmic coincidences? The most radical theories venture even further. What if dark matter wasn't just a spectator but an active participant? Some physicists explore scenarios where dark matter particles occasionally annihilate each other, releasing bursts of radiation. In the dense environments of early galaxies, these collisions might have been frequent enough to contribute significant ionizing energy. Others speculate about primordial black holes, dark matter candidates the size of asteroids evaporating via Hawking radiation and flooding their surroundings with ionizing particles. These ideas sit firmly in fringe territory, but they highlight how little we truly understand about dark matter's potential to shape cosmic history. For now, the evidence remains circumstantial. Telescopes like the James Webb Space Telescope and upcoming radio observatories could change that by mapping the temperature fluctuations of hydrogen gas from the reionization era. A slight excess of warmth in unexpected places might betray dark matter's hidden influence. Until then, the question lingers: did the universe's unseen majority quietly tilt the scales during one of its most pivotal transitions? The answer could rewrite not just the story of reionization, but our entire understanding of how light and darkness dance together across the cosmos. If early galaxies were the engines of reionization, their fuel was ultraviolet photons, particles of light with enough energy to strip electrons from hydrogen atoms. But here's the catch: not all those photons made it out of their galactic nurseries. The fraction that escaped into intergalactic space, known as the escape fraction, is one of the most elusive numbers in cosmology. Picture a bustling city at night. Some buildings blast light through open windows while others keep their curtains tightly drawn. Across the early universe, galaxies behaved similarly, some leaking torrents of ionizing radiation, others holding nearly all of it captive. This randomness isn't just a curiosity, it's the key to understanding why reionization unfolded so unevenly and why our models still struggle to pin it down. Measuring the escape fraction feels like trying to count fireflies through a thunderstorm. The photons that matter, those capable of ionizing hydrogen, are absorbed by interstellar gas almost instantly, meaning only a tiny sliver slip free. Even worse, our telescopes can't directly observe these photons from galaxies in the reionization era. The universe's expansion has stretched their light into infrared wavelengths, where atmospheric interference and instrumental noise drown out their faint signals. Instead, astronomers rely on clever workarounds, like studying younger galaxies that resemble their ancient counterparts or hunting for telltale chemical signatures in their spectra. Each method carries its own uncertainties, leaving the escape fraction frustratingly fuzzy somewhere between 5 and 20%, depending on whom you ask. Why such wild variation? The answer lies in the chaotic environments of early galaxies. Unlike modern spirals with orderly spiral arms, these primordial giants were clumpy, turbulent beasts. Dense pockets of gas formed natural roadblocks, trapping ionizing radiation before it could escape. But when a massive star exploded as a supernova, its shockwaves could carve tunnels through the chaos, opening fleeting escape routes for photons. Galaxies with frequent stellar explosions might have leaked radiation like sieves, while quieter ones retained their ionizing light like cosmic vaults. Even something as subtle as a galaxy's angle relative to Earth could skew measurements. A galaxy-tipped edge on might appear dimmer in escaping photons simply because its radiation had to plow through more gas to reach us. The implications ripple across cosmology. If most galaxies had low escape fractions, reionization would have required an impossibly high number of early stars to compensate, more than current models allow. But if even a small fraction of galaxies leaked profusely, they could have done the heavy lifting, ionizing vast regions while their neighbors contributed little. This might explain the patchiness of reionization, bubbles of ionized gas expanding around rare, leaky galaxies, leaving others in shadow. The puzzle deepens when considering dwarf galaxies. Though small and faint, their sheer numbers could have made them dominant players if their escape fractions were high enough. Recent observations suggest some dwarfs let nearly half their ionizing photons escape, a staggering figure that could rewrite the reionization playbook. Perhaps the greatest twist is how escape fractions might have changed over time. Early galaxies, rich in pristine gas, were likely leakier as their stars formed in less dusty environments. But as generations of supernova polluted their surroundings with heavy elements, gas became better at trapping radiation. This feedback loop, where stars both create and destroy escape paths, adds another layer of complexity to the reionization timeline. It's a cosmic catch-22. The very process that ionized the universe may have also made subsequent ionization harder. Unlocking this mystery will require telescopes capable of dissecting the faintest whispers of light from the cosmic dawn. The James Webb Space Telescope is already hunting for indirect clues, like the ratio of ionized helium in early galaxies, a potential marker of escaping photons. Meanwhile, upcoming radio arrays will map the distribution of neutral hydrogen, offering a backdoor way to estimate how much radiation must have leaked to create the patterns we see. Until then, the escape fraction remains one of reionization's most stubborn variables, a reminder that even the smallest uncertainties can cast the longest shadows across our understanding of the universe's first light. As ionized bubbles expanded across the early universe, they didn't just push against the darkness, they eventually collided, merged, and stitched together the first connected webs of light. This brief but pivotal moment, known as the overlap phase, marks the point when isolated pockets of ionization finally touched, like raindrops blending into a puddle. Yet for all its significance, this transition remains one of reionization's most enigmatic chapters. Simulations consistently hit a wall when trying to recreate it, producing either implausibly smooth mergers or chaotic shredding of gas clouds that don't match observational clues. The truth, it seems, lies somewhere in the messy interplay of forces we're still struggling to quantify. Take the simplest assumption that ionized bubbles grew uniformly until their edges met. In reality, the overlap phase was anything but orderly. Some bubbles expanded faster than others, their edges warped by the gravitational pull of unseen dark matter structures. When they finally connected, the collisions weren't gentle handshakes, they were cosmic traffic jams, with streams of radiation and shocked gas ricocheting in unpredictable directions. Simulations that treat the universe as a uniform soup fail spectacularly here, missing the tangled filaments of matter that channeled and redirected ionization fronts like rivers diverting floodwaters. The biggest headache for astronomers, the Lyman-alpha forest data. Those absorption lines in quasar spectra don't show a clean, instantaneous drop in neutral hydrogen as overlap theory predicts. Instead, they reveal lingering wisps of gas stubbornly clinging to neutrality, even in supposedly fully reionized regions. It's as if the cosmic fog didn't lift uniformly but left behind ghostly tendrils, like morning mist lingering in valleys after the sun has risen. Some theorists argue this means overlap wasn't a single event but a drawn-out process, with islands of neutrality surviving for millions of years in cosmic dead zones, places where radiation from multiple sources cancelled out or where dense gas clouds absorbed photons faster than they could be replenished. Then there's the temperature puzzle. When ionized bubbles merged, the energy released should have left scars, subtle heating patterns in the leftover hydrogen. Yet when astronomers measure the temperature of gas from this era using the cosmic microwave background's polarization, the readings are all over the map. Some regions appear inexplicably hotter than models allow, hinting at violent mergers or perhaps unknown energy sources at play. Others are suspiciously cool, as if something may be early magnetic fields or turbulence siphoned off energy during the overlap process. The stakes go beyond mere curiosity. How overlap occurred shaped the large-scale structure of the universe. Smooth, uniform mergers would have created even conditions for galaxy formation, while chaotic ones might have seeded the vast cosmic voids and filaments we see today. Some even speculate that these collisions triggered secondary waves of star formation, as compressed gas at bubble boundaries finally reached critical density. Telescopes like the Square Kilometre Array aim to test this by mapping the distribution of neutral hydrogen with unprecedented precision, hunting for fossilized bubble boundaries frozen in time. Until then, the overlap phase remains a cosmic Rorschach test. Every observer sees patterns, but the full picture eludes us all. Perhaps the most humbling realization is that we might be missing a fundamental piece of physics. Current models rely on known interactions between light and matter, but what if overlooked phenomena like quantum fluctuations in the early plasma or interactions with dark matter altered the overlap process in ways we can't yet simulate? The answers, if they come, won't just solve a puzzle about the past. They'll reveal how the universe stitched itself together, one ionized bubble at a time, to become the luminous web we call home. While hydrogen reionization set the early universe ablaze, helium, the cosmos' second lightest element, played by different rules. Unlike hydrogen, which shed its electrons relatively quickly under the barrage of ultraviolet light, helium clung to its particles stubbornly, requiring far more energy to ionize. This delay creates a fascinating puzzle. If the first stars and galaxies were powerful enough to strip hydrogen bare, why did helium's liberation take hundreds of millions of years longer? The answer lies in the shifting nature of cosmic power sources, revealing a universe where the very engines of light evolved dramatically over time. The key difference comes down to energy thresholds. Hydrogen's single electron pops free when hit by photons with energies just shy of 14 electron volts, roughly what hot, young stars produce in abundance. But helium's 2 electrons demand more extreme conditions. The first electron breaks loose at 25 electron volts, achievable by many early stars. The second, however, holds on until photons pack a staggering 54 electron volts, pushing into the realm of extreme ultraviolet and X-ray radiation. For much of the reionization era, such energetic photons were in short supply. The universe needed to forge even fiercer furnaces before helium could fully join the ionized cosmos. That turning point came with the rise of quasars, as supermassive black holes at galactic centers began guzzling matter at unprecedented rates. They unleashed torrents of high-energy radiation, finally cracking helium's second electron barrier. Yet here's the twist: helium reionization didn't happen uniformly. Quasars were rare and clustered along the cosmic web's filaments, leaving vast regions where helium remained neutral well into the universe's middle age. Even today, traces of this patchiness linger in the so-called helium Lyman-alpha forest, spectral shadows hinting at incomplete ionization, but the plot thickens when we compare timelines. While hydrogen reionization wrapped up around 1 billion years after the Big Bang, helium's final ionization phase didn't conclude until nearly 3 billion years, in a staggering delay that challenges conventional wisdom. Some models suggest early quasars weren't the only players. Perhaps accreting black holes in dwarf galaxies or even exotic objects like intermediate mass black holes contributed bursts of hard radiation. Others propose that the gradual buildup of X-ray binaries, pairs of stars where one siphons material onto a neutron, star or black hole, created a steady background glow that chipped away at helium's defenses over eons. This layered timeline offers a unique window into cosmic evolution. The delay between hydrogen and helium reionization mirrors the universe's shift from starlight dominance to black hole-driven energy. It's as if the cosmos matured through distinct phases. First, the raw fury of massive stars, later, the refined brutality of black holes. And somewhere in that transition, the balance of power shifted enough to finally pry loose helium's most stubborn electrons. The implications stretch beyond mere chronology. Since helium makes up nearly 10% of the universe's normal matter, its ionization state influenced how galaxies cooled, how gas flowed, and even where future stars could form. Yet mysteries remain. Why do some regions show evidence of early helium ionization before quasars were supposedly numerous enough? Could population 3 stars have briefly punched above their weight, or does this hint at unknown high-energy phenomena in the early cosmos? And how did the gradual ionization of helium feed back into galaxy formation, potentially altering the very structures that drove the process? These questions tie helium's story back to hydrogen's, revealing not 2 separate events, but chapters in a single, sweeping narrative of cosmic awakening. One where every element, from the lightest to the heaviest, carries clues to the universe's most transformative era. The boundary between the cosmic dawn and the reionization era might seem crisp in textbooks, a neat dividing line between the universe's first starlight and its later transformation by that light. But the cosmos rarely obeys our tidy categories. Recent evidence suggests these epochs didn't just follow one another. They bled together, with the earliest stars flickering to life while vast regions of space still slumbered in darkness. This blurry handoff raises profound questions. Did reionization begin as a whisper during the cosmic dawn, building to a crescendo later? Or did the universe experience multiple false starts before committing to light? 21-centimeter radio signals could untangle this cosmic knot. When hydrogen atoms drift through space, their electrons occasionally flip spin states, emitting faint radio waves at a wavelength of 21 centimeters. During the cosmic dawn, before starlight flooded the cosmos, these signals would have been strong and clear, a direct broadcast from pristine gas clouds. As reionization progressed, however, ionizing radiation would have silenced them, stripping away the neutral hydrogen needed to produce the signature. The timing of this radio fade-out holds the key. If we detect patches where 21-centimeter signals vanish earlier than expected, it could mean some regions began reionizing while others were still witnessing their first dawn. The challenge lies in reading these ghostly radio whispers. Earth's atmosphere and human-made interference drown out the faint signals, requiring telescopes like the Hydrogen Epoch of Reionization Array to listen from remote deserts. Early results already paint a chaotic picture. Some areas of the early universe appear to have switched off their 21-centimeter emissions surprisingly early, while others clung to neutrality long after their neighbors had brightened. This patchiness implies the cosmic dawn didn't end abruptly. It sputtered out in fits and starts, with reionization advancing unevenly across the cosmic frontier. The implications rewrite our understanding of the universe's adolescence. If the first stars and their ionizing aftermath overlapped significantly, it means early galaxies didn't wait for ideal conditions. They formed and transformed their surroundings simultaneously. This could explain why some ancient galaxies appear oddly mature when we catch glimpses of them. They weren't just products of their era, but active shapers of it. The 21-centimeter data also hints at environmental factors we've yet to account for. Perhaps dark matter densities or primordial magnetic fields that made certain regions ripe for early ionization while others resisted. Yet contradictions linger. Some models predict the cosmic dawn's 21-centimeter signal should show a distinctive dip as X-rays from early black holes heated the gas, a phenomenon we've yet to observe clearly. Does this mean our timeline is off, or that unknown processes mask the expected pattern? The answer could redefine not just when these eras transitioned, but how we classify cosmic epochs altogether. After all, nature doesn't care for human-made labels. What we see as distinct chapters might simply be the universe's way of telling one continuous, spectacular story. Upcoming radio telescopes promise to sharpen this blurry picture. By mapping the 21-centimeter signal in 3 dimensions across billions of light years, they'll trace how light first infiltrated the cosmic dark, not as a uniform wave, but as a creeping tide, advancing here while retreating there. And somewhere in that intricate dance between the first starlight and the great ionization that followed, lies the true origin story of everything we see around us today. The Milky Way's miniature companions shouldn't exist, at least, not as we see them today. Scattered like cosmic fossils around our galaxy, dwarf satellite galaxies such as Sculptor and Fornax appear ancient, their stars bearing the chemical marks of extreme old age. Here's the puzzle. Many of these stars formed during or even before the Cosmic Reionization Era, yet they somehow survived the scorching ultraviolet radiation that should have sterilized their gas and halted star formation. It's as if these fragile cosmic villages endured a wildfire meant to wipe them out, leaving astronomers to wonder. Did they find shelter in the shadows, or is our understanding of reionization's timeline fundamentally flawed? One clue lies in their locations. These dwarfs orbit far from the Milky Way center, often in regions where reionization may have arrived late. Picture the early universe as a storm-swept ocean. While massive galaxies closer to matter-rich filaments were battered by ionizing radiation early on, quieter backwaters might have retained neutral hydrogen longer, allowing star formation to persist. Some simulations suggest these sheltered pockets could have lagged behind the broader reionization timeline by hundreds of millions of years, creating cosmic time capsules where conditions resembled the pre-reionization era long after most of the universe had moved on. The dwarfs we see today might be the lucky survivors of these delayed zones, their stars forming in relative isolation while the cosmic storm raged elsewhere. But there's a wrinkle. The chemical makeup of these stars tells a more complicated story. Many contain surprisingly few heavy elements, a hallmark of stars born from nearly pristine gas, which should have been vanishingly rare after reionization's intense radiation began recycling metals through supernova. This suggests some dwarfs didn't just form in sheltered corners. They may have formed twice, an initial burst during the cosmic dawn, then a mysterious hiatus during peak reionization, followed by a late resurgence as gas somehow reaccreted. How these galaxies managed to reclaim their gas after the universe's ultraviolet background should have blown it away remains unknown. Some theorists propose dark matter's gravitational grip shielded gas clouds just enough for them to condense again, while others speculate that cold flows of gas from the cosmic web pierced through ionized regions, delivering fresh fuel against all odds. The implications ripple outward. If these dwarfs truly formed stars continuously despite reionization, our estimates for when the epoch ended might need revising. Or worse, we might be missing a key mechanism that allowed small galaxies to resist ionization's effects. Even stranger, some ultra-faint dwarfs display star formation histories so prolonged they seemingly defy all models. Take Segway 1, a dim satellite with stars spanning over 13 billion years in age. Its persistence hints at environments where reionization's impact was oddly muted, as if pockets of the early universe operated under different rules. Could magnetic fields or turbulence have played unappreciated roles? Or does this paradox point to something deeper, like variations in the ultraviolet background itself, with some regions remaining eerily quiet long after others blazed with radiation? Answers might lie in upcoming surveys of the Milky Way's outer halo. By mapping the motions and compositions of ancient stars in these dwarfs, astronomers hope to reconstruct their orbital histories, essentially tracing their paths back to the reionization era to see where they weathered the storm. Meanwhile, telescopes like the James Webb Space Telescope are probing similar dwarf galaxies in distant clusters, searching for analogues that might reveal whether the Milky Way's satellites are unique or part of a broader cosmic pattern. What they find could rewrite not just the story of these galactic minnows, but our understanding of how light first sculpted the universe's smallest structures. After all, if the tiniest galaxies could hold secrets this profound, what else might we have missed in the shadows of cosmic history? Among the faintest and most ancient relics drifting through the cosmos, ultra-faint dwarf galaxies glow like dying embers of the universe's first fires. These ghostly collections of stars, some containing fewer stars than a single globular cluster, should have been obliterated by the fierce radiation of reionization. Yet here they are, surviving against all odds, their chemical compositions frozen in time like cosmic time capsules. Their very existence poses a tantalizing question. How did these fragile islands of stars endure an era that should have ripped them apart? The answer may lie in their poverty. Ultra-faint dwarfs are the most metal-poor galaxies known, their stars forged from gas nearly untouched by heavy elements. This pristine composition suggests they formed early, perhaps even before reionization began, from clouds of hydrogen and helium so pure they resemble the raw ingredients of the Big Bang itself. Unlike their richer cousins, these galaxies never hosted the scorching, short-lived stars that flood space with ionizing radiation. Instead, they simmered quietly, their modest stellar populations barely disturbing the surrounding gas. That very dimness might have been their salvation. While brilliant galaxies drew the attention of reionization's destructive forces, ultra-faint dwarfs could have slipped under the radar, their meek starlight too feeble to attract the ultraviolet onslaught that sterilized larger systems. But their survival isn't the only puzzle. The star formation histories of these dwarfs read like fragmented diaries from the cosmic dawn. Some show evidence of a single, ancient burst of star activity before abruptly falling silent, as if reionization's tide finally reached them and snuffed out their gas supply forever. Others display sporadic flickers of star birth stretched over billions of years, hinting at pockets of gas that somehow dodged ionization or trickled back in against the odds. The most enigmatic cases, like Segway 1 and Triangulum 2, contain stars so old they predate reionization entirely, yet their orbits suggest they've been orbiting the Milky Way for eons, surviving multiple passes through our galaxy's disruptive halo. How they retained their fragile stellar populations through such turmoil defies easy explanation. Chemically, these galaxies are time machines. Their stars lack the heavy elements forged in supernova, meaning they formed before successive generations of stars could pollute their birth clouds. This makes them ideal laboratories for studying the conditions of the early universe. When astronomers analyze their light, they're effectively reading the cosmic recipe from a time before reionization reshaped everything. Even stranger, some ultrafaints show unexpected spikes in certain elements like our process metals, suggesting they were seeded by a single cataclysmic event, perhaps a neutron star collision in their distant past. These anomalies could reveal how quickly the first heavy elements spread through the primordial cosmos, painting a picture of a universe far more dynamic in its youth than we ever imagined. Yet contradictions abound. If these galaxies are such perfect relics, why do some display subtle signs of tidal disruption, stretching and twisting that implies past encounters with larger structures? And why do a handful, like Leo T, still cling to wisps of gas and even show signs of recent star formation, despite floating in a universe that should have stripped them bare eons ago? The answers might rewrite our understanding of reionization's reach. Perhaps the process was patchier than we thought, leaving behind sheltered valleys where gas could linger. Or maybe dark matter played a stealth role, its gravitational grip shielding these dwarfs just enough to preserve their delicate balance between survival and oblivion. The key to unraveling this enigma lies in the next generation of telescopes. Projects like the Vera Rubin Observatory will scour the skies for more of these cosmic fossils, potentially doubling the known population of ultrafaint dwarfs. Meanwhile, the James Webb Space Telescope peers into their ancient stars, decoding their elemental makeup with unprecedented precision. Each discovery peels back another layer of the mystery, revealing not just how these galaxies endured, but how the universe's most fragile structures can outlast its most violent transformations. Their faint glow reminds us that sometimes the quietest voices carry the loudest echoes of history. The cosmic microwave background isn't just a snapshot of the universe's infancy, it's a palimpsest, layer upon layer of subtle imprints left by every cosmic upheaval that followed the Big Bang. Among the faintest of these fingerprints are the polarization patterns etched by reionization, whispers of a time when the first starlight tore through the cosmic fog. These delicate swirls, known as E-modes, act like a forensic tape stretched across 13 billion years, capturing the moment when the universe switched from neutral to ionized. But like any ancient text, decoding them comes with its own set of riddles. E-modes form when free electrons scatter the CMB's light, leaving behind a distinctive polarization signature as they're buffeted by the turbulence of reionization. Think of it as sunlight glinting off choppy water. The pattern of ripples tells you not just that the wind was blowing, but how hard and for how long. By measuring these polarized swirls, astronomers can estimate when reionization began, how long it lasted, and even how patchy the process was. The Planck satellite's readings suggest the bulk of reionization happened relatively quickly, wrapping up by the time the universe turned 1 billion years old. But here's where the mystery deepens. Those same E-modes also hint at earlier flickers of ionization, as if the universe's lights tried to turn on centuries before the main event. Disentangling these clues is like trying to reconstruct a symphony from the echoes bouncing off a single wall. The E-modes we see are a blend of signals, some from reionization, others from the primordial density fluctuations of the Big Bang itself. Teasing them apart requires statistical acrobatics, with cosmologists running thousands of simulations to match the observed patterns. The results point to a reionization timeline that's neither smooth nor uniform. Some models suggest an early, tentative phase where massive population 3 stars ionized small bubbles around themselves, followed by a delayed but more decisive push from galaxies and quasars. Others argue for a single prolonged struggle, with the universe flickering in and out of ionization like a faulty neon sign. The contradictions don't end there. While E-modes broadly align with estimates from quasar absorption lines and 21-centimeter data, they paint a slightly different portrait of reionization midpoint. Planck's data implies a later, more abrupt transition than some galaxy surveys suggest, a discrepancy that could mean our models are missing a key ingredient. Perhaps dark matter played a subtler role than we thought, or maybe early magnetic fields altered how ionization fronts propagated. There's even a fringe hypothesis that decaying exotic particles injected extra energy at critical moments, skewing the polarization signals we observe today. What makes these clues so tantalizing is their universality. Unlike quasars or galaxies, which only sample narrow sightlines, the CMB's polarization blankets the entire sky, offering a global census of reionization impact. Future observatories like the Simons Observatory and CMB S4 aim to map E modes with unprecedented precision, potentially spotting the faint B modes that could betray reionization's earliest stirrings. Until then, these polarized whispers remain a cosmic Rorschach test. Every team sees a slightly different story in the swirls. One thing's certain: whatever erased the universe's darkness left behind a signature we're only beginning to decipher, and its full story might rewrite how we understand the dawn of light itself. Some of the universe's deepest secrets aren't written in light, they're written in shadows. The Gunn-Peterson trough is one such cosmic silhouette, a blank stretch in the spectra of distant quasars where light should be but isn't. Picture a quasar's brilliant beam traveling across the universe, only to hit a wall of neutral hydrogen, gas so thick it absorbs nearly all ultraviolet light at a specific wavelength. This abrupt, dark gap in the spectrum is like a fingerprint left by the universe's primordial fog. A smoking gun proving that vast stretches of space once brimmed with untouched hydrogen before reionization scrubbed them clean. But here's what makes this trough so puzzling. It's virtually absent in quasars from the modern universe. Peer at a quasar born after reionization, and its spectrum flows smoothly, uninterrupted by those deep absorption lines. The difference between these two snapshots, one with a trough, one without, marks the moment the universe transitioned from darkness to light, or at least that's the textbook explanation. Dig deeper and the story gets murkier. Some quasars at the edge of reionization show troughs that aren't completely black but flecked with faint light, as if the gas wasn't uniformly neutral. Others reveal troughs that vanish unexpectedly early, hinting at regions where reionization leapt ahead of schedule. These anomalies force us to ask, was the Gunn-Peterson trough truly a global phenomenon or just a patchwork of local shadows? The trough's depth also holds surprises. In a perfectly neutral universe, it should be absolute, a total blackout at that critical wavelength. Yet even the most distant quasars, those whose light left mere hundreds of millions of years after the Big Bang, often show troughs with subtle leaks. Some theorists argue this means the universe was never fully neutral. Fierce radiation from the earliest stars and galaxies might have created ionized bubbles long before the official reionization era began. Others think the answer lies in the clumpiness of primordial gas. If neutral hydrogen wasn't evenly distributed but gathered in dense clouds with gaps between them, some quasar light could have slipped through the cracks, creating the illusion of partial ionization. Then there's the mystery of the trough's edges. The transition from trough to no trough isn't always sharp. Some quasars display a gradual fading of the absorption line, as if the gas in their path was ionized unevenly along the line of sight. This blurriness challenges the idea of reionization as a clean, global event. Instead, it paints a picture of a chaotic frontier where ionized and neutral regions tangled together like threads in a cosmic tapestry. The James Webb Space Telescope is now peering at these spectral shadows with unprecedented clarity, searching for faint variations that could reveal how reionization rippled through the universe's gas. Perhaps the most tantalizing clue lies in quasars that shouldn't show a trough at all. A handful of extremely distant quasars, born well into the reionization era, still display Gunn-Peterson absorption as if they're gazing through lingering pockets of neutral gas. These outliers suggest reionization didn't end with a uniform flip of a switch. Some stubborn regions might have held out far longer, their hydrogen resisting ionization long after the rest of the universe had brightened. What shielded these cosmic holdouts? Dense gas clouds, sheltering magnetic fields, or something even stranger, lurking in the interplay between matter and the dark cosmos we've yet to map? The Gunn-Peterson trough isn't just a relic of the past. It's a challenge to our models, a reminder that the universe's grandest transformations rarely follow simple scripts. Every quasar spectrum we analyze adds another brushstroke to the portrait of reionization, one that's proving far more textured and far more enigmatic than we ever anticipated. The early universe was supposed to be a chemical blank slate, vast clouds of pure hydrogen and helium swirling in the darkness, untouched by heavier elements forged in stellar furnaces. Yet when astronomers analyze gas clouds from the reionization era, they stumble upon a paradox. Some appear suspiciously clean, lacking even trace metals that should have been seeded by the first supernova. This absence raises a haunting question. Were these clouds truly pristine, frozen relics of the Big Bang itself? Or are we missing something fundamental about how metals spread through the infant cosmos? Take the Lyman-alpha forest clouds, for instance. These ancient wisps of gas, seen as absorption lines in quasar spectra, often show metal abundances thousands of times lower than modern interstellar space. At face value, they seem like perfect time capsules from before the first stars polluted the universe. But here's the catch: even the earliest supernova, those from short-lived population 3 stars, should have sprayed heavy elements like carbon and oxygen far and wide. Simulations suggest their explosive deaths would have laced nearby gas with detectable metals within just a few million years. So why do some reionization era clouds register as chemically virgin? One possibility cuts to the heart of cosmic geography. The early universe wasn't a well-mixed soup. It had structure, with dense filaments of gas weaving through vast, empty voids. Metals ejected by the first stars might have concentrated along these cosmic highways, leaving the hinterlands untouched. Imagine sprinkling salt into a swirling bathtub. Some pockets stay fresh while others grow briny. This uneven distribution could explain why certain sightlines through the reionization era appear metal-free, while others, like those piercing early galaxy clusters, show chemical enrichment. Then there's the detective's dilemma. Our tools might be missing the clues. Current telescopes struggle to detect metals below 1/10,000th of solar abundance in these distant clouds. That's like trying to spot a single grain of sand in an Olympic swimming pool. Worse, some elements could be hiding in plain sight, locked in dust grains too cold to emit, or ionized into states that don't absorb light at wavelengths we typically observe. The James Webb Space Telescope is starting to change this. Its infrared eyes capable of spotting elusive molecular compounds like metal hydrides that previous surveys overlooked. Already, it's found whispers of oxygen in clouds once deemed pristine, hinting that the metal-free label might say more about our limitations than the early universe's chemistry. The stakes go beyond mere bookkeeping. If pockets of truly primordial gas survived well into the reionization era, they could have birthed late-forming population 3 stars. Those mythical metal-free giants thought to exist only in the universe's first 100 million years. Finding even one such star today would rewrite stellar physics, offering a glimpse of how stars behave when untempered by heavy elements. Some theorists speculate that the faintest dwarf galaxies might harbor these relics, their slow, isolated evolution preserving conditions closer to the cosmic dawn than anywhere else. Yet contradictions persist. A handful of quasar spectra reveal clouds with bizarre chemical ratios, traces of nitrogen without accompanying carbon, or odd silicon isotopes that shouldn't form in standard supernova. These anomalies suggest alternative enrichment sources, perhaps pair instability supernova from ultra-massive population 3 stars, or even exotic processes involving dark matter decay. Each possibility opens new doors to understanding how the universe's first elements spread, or failed to spread through the primordial dark. the mystery of metal-free gas ultimately forces us to confront how little we know about pollution on cosmic scales. Did metals circulate efficiently, or did vast regions remain chemical deserts long after the first stars died? The answer could redefine not just our picture of reionization, but the very conditions under which the earliest galaxies took shape. After all, the absence of metals doesn't just mark a lack, it's a silent testament to the universe's struggle to transform from simplicity to complexity, one atom at a time. Reionization's greatest accounting mystery boils down to a simple question: did the universe's early power sources produce enough ionizing photons to strip every last hydrogen atom of its electron? When astrophysicists crunch the numbers, the ledger never quite balances. The known contributors, early galaxies, quasars, population, 3 stars fall short by up to 50% in some estimates, leaving a glaring gap in the cosmic energy budget. It's as if we've discovered a 13th century cathedral, but only half the bricks needed to build it, forcing us to ask, what invisible masons completed the job? Galaxies shoulder much of the blame for this discrepancy. While they're prolific UV factories, their output is hobbled by 2 factors: escape fractions and dust. Only a fraction of their ionizing photons break free of galactic gas clouds, and those that do must contend with interstellar dust grains that absorb them like cosmic sponges. Even after accounting for these losses, models suggest the brightest galaxies could only have ionized about 30% of the universe's hydrogen. Quasars, though individually powerful, were too rare to pick up the slack, their contribution likely capped at 20%. That leaves half the universe's ionization unaccounted for, a deficit that grows wider when considering how inefficiently photons were recycled in the early cosmos. Enter the dark horses of reionization. One promising candidate hides in plain sight: dwarf galaxies. Though individually faint, their sheer numbers could tip the scales. Recent James Webb observations reveal ancient dwarfs pumping out ultraviolet radiation at rates up to 10 times higher than predicted, their small sizes allowing photons to escape more easily. If these tiny power plants were thousands of times more abundant than quasars, their collective glow might patch the budget gap, yet even then anomalies persist. Certain regions of the early universe appear over-ionized, as if blasted by radiation from no known source. This inconsistency has birthed wilder theories. Could mini-quasars, dim, numerous black holes too small to qualify as full quasars, have lurked unseen in early galaxies? Their combined X-ray output might have subtly heated hydrogen, lowering the energy needed for ionization. Others point to hypothetical decaying particles like sterile neutrinos or actions, whose death throes could have released cascades of ionizing energy. Even primordial black holes, evaporating via Hawking radiation, get a speculative nod. Their final bursts might have peppered the cosmos with just enough photons to push reionization over the edge. The solution might be messier than any single explanation. Perhaps reionization wasn't powered by a dominant source, but by a chaotic ensemble: cast galaxies, quasars, dwarfs, and exotic phenomena, all playing intermittent roles. Each new observation adds complexity: galaxies with irregular star formation bursts, quasars flickering on and off, or even undiscovered classes of objects glowing in far ultraviolet. Until we can census every photon source from the cosmic dawn, the ledger will remain stubbornly unbalanced, a reminder that the universe's greatest transformations often leave room for the unexplained. Reionization wasn't just a one-way street, it triggered a cosmic catch-22 that may have slammed the brakes on the very stars and galaxies driving it. As ultraviolet radiation flooded the early universe, it didn't just strip electrons from atoms, it superheated the remaining gas, making it too energetic to collapse into new stars. This feedback loop created a paradox. The same light that fueled the universe's awakening also starved it of the raw materials needed to keep building. The question isn't just whether this happened, but how unevenly it played out and whether some galaxies found loopholes in the physics that let them thrive while others stalled. Take the temperature of the intergalactic medium before and after reionization, and the difference is staggering. Neutral hydrogen in the cosmic dawn hovered around a chilly 50 Kelvin, cold enough for gravity to clump it into star-forming clouds. But once ionized, that same gas could soar to over 10,000 Kelvin, puffing up like a thermal blanket that smothered galaxy growth. Simulations show smaller galaxies hit hardest. Their shallow gravitational wells couldn't hold onto the scorching gas, leaving them stranded as ghost towns with no fuel for new stars. This might explain why we see so few ultra-faint dwarf galaxies today. Reionization didn't just illuminate the universe, it sterilized its smallest structures. Yet the story isn't so tidy. Certain galaxies, like those in dense protoclusters, appear to have weathered the storm. Their deeper gravitational potentials acted like pressure cookers, holding gas tight despite the heat. Others might have benefited from timing, forming stars rapidly before the ionizing wavefront arrived, then going dormant like seeds waiting for rain. The real outliers are dark galaxies, clouds of neutral hydrogen detected through their Lyman-alpha glow, but seemingly devoid of stars. These cosmic anomalies could be relics of reionization fallout, gas that was either too hot to collapse or protected in shadowy pockets where radiation never fully penetrated. The feedback loop's fingerprints might also hide in modern galaxies' chemical makeup. Stars born before reionization, so-called population 2 stars, contain fewer heavy elements than later generations, suggesting their birth clouds were less polluted by supernova. If reionization throttled star formation early, it could have artificially capped metal production in some galaxies, leaving behind this chemical time stamp. Stranger still, a few galaxies like Zwicky 18 defy expectations by forming stars in near-pristine gas billions of years after reionization ended. Did they somehow reset the clock, or did they orbit in cosmic dead zones where the feedback loop never took hold? Unraveling this puzzle requires peering into the reionization era's messy aftermath. Radio telescopes like ALMA are mapping the cold gas reservoirs in ancient galaxies, hunting for clues about how quickly they cooled post-ionization. Meanwhile, theorists explore wild cards like turbulent gas flows or early magnetic fields that could have shielded some regions from the worst effects. The answer won't just solve a cosmic whodunit. It'll reveal whether reionization was the universe's strict regulator, enforcing a galactic hierarchy we still see today, or if chance and chaos played bigger roles than we ever imagined. One thing's certain, the same fire that lit the cosmos also left burns whose scars were only beginning to trace. Amid the cosmic fireworks of reionization, where most galaxies formed in a frenzy of early starlight, a handful of celestial rebels took their time. These late bloomers galaxies that ignited hundreds of millions of years after their peers shouldn't exist according to standard models. Their very presence raises a tantalizing possibility. Did some corners of the universe resist reionization's transformative tide, preserving pockets of primordial gas where galaxies could form against all odds? Or are we looking at an entirely new class of objects that played by different rules? Take the enigmatic galaxy Amesison 1420, spotted by the James Webb Space Telescope. Born nearly 800 million years after the Big Bang, well into the reionization era's final act, it glows with the telltale signatures of active star formation, as if it hit the cosmic snooze button while others raced ahead. Stranger still, its chemical makeup mirrors galaxies from earlier epochs, rich in hydrogen but eerily devoid of heavier elements. This anomaly suggests it formed from gas that somehow avoided pollution by earlier stellar generations, like a pristine ice cube surviving in a stirred cocktail. The most compelling explanation, it may have grown in a cosmic backwater where reionization arrived fashionably late. a sheltered valley where gas remained cool and neutral long enough for delayed galaxy birth. But not all latecomers fit this mold. Some, like the recently discovered galaxy JWST, display bizarre hybrid traits, stars as old as the universe itself alongside newborn stellar nurseries. This suggests they didn't simply form late, they formed in spurts, with initial star formation halted abruptly by reionization's heat, only to reignite eons later when cold gas somehow returned. How these galaxies reclaimed their fuel remains speculative. Perhaps filaments of the cosmic web funneled fresh gas into their cores, or mergers with gas-rich dwarfs replenished their reserves. Others might owe their delayed ignition to dark matter halos massive enough to recapture ionized gas once reionization's ultraviolet background faded slightly, allowing cooling and collapse to resume. The implications ripple beyond chronology. If late-forming galaxies thrived in reionization's shadow, their existence could rewrite how we map the era's progress. Current models assume a relatively uniform timeline, but these stragglers hint at a patchwork universe where ionization advanced like a creeping frost, leaving isolated refuges untouched. Radio telescopes scanning for 21-centimeter signals might soon detect these holdout regions' neutral hydrogen pockets lingering like cosmic dew in the morning light of reionization's end. Yet the most radical possibility is that we're seeing a forgotten chapter of galaxy formation. Some late bloomers exhibit structures unlike anything in the early universe, faint, diffuse disks with star formation rates too steady for their turbulent era. Dubbed dark horse galaxies, they may represent a rare breed that formed without the violent bursts typical of their peers, their gentle birth preserving gas too efficiently for reionization to fully disrupt. As telescopes probe deeper, each discovery blurs the line between cosmic exception and textbook revision, reminding us that even the universe's most transformative eras left room for outliers to scribble their own rules. The cosmic web wasn't just a silent scaffold for galaxies, it was the universe's grand canal system, directing the flow of ionizing radiation like water through ancient aqueducts. Picture those vast filaments of dark matter and gas, some thinner than a galaxy's width yet stretching billions of light years, weaving a labyrinth where radiation could travel far beyond its sources. But here's the twist. This intricate network didn't just speed up reionization uniformly. It created cosmic shortcuts and roadblocks, turning the process into a turbulent relay race where some regions blazed bright early while others lagged in shadow. Simulations reveal a paradoxical dance. Along dense filaments, radiation surged efficiently, ionizing gas at astonishing distances as photons bounced from hydrogen atom to hydrogen atom in a process called photon surfing. These pathways acted like fiber optic cables, funneling light from early galaxies into the void. Yet the same filaments also sheltered pockets of neutrality, their dense cores so packed with gas that even the fiercest ultraviolet onslaught took longer to penetrate. It's as if the cosmic web was both highway and hiding place, accelerating reionization in one breath while resisting it in the next. The real surprise came when models factored in the web's voids. These vast, empty regions, some spanning hundreds of millions of light years, were assumed to be quick ionization zones with little gas to block radiation. Instead, they behaved like cosmic eddies where photons languished without atoms to interact with, slowing reionization's advance. Meanwhile, the intersections of filaments, those bustling galactic crossroads, became hotspots of ionization, their abundant galaxies teaming up to blast away surrounding hydrogen like a crowd chipping at an iceberg. But the web's influence didn't stop there. Gravity's subtle tugs on the filaments warped the paths of ionizing photons, bending them around massive galaxy clusters or redirecting them toward underdense regions. Some simulations even suggest that early magnetic fields, amplified by the web's structure, may have further steered radiation in unpredictable ways. The result, a reionization map resembling less a spreading wildfire and more a capricious flood, its tides dictated by the unseen topography of dark matter and gas. Observational clues add another layer of intrigue. Quasars whose light pierced multiple filaments show uneven absorption patterns, some spectral lines nearly wiped clean, others stubbornly dark, as if the cosmic web's strands alternately welcomed and barred radiation's advance. Meanwhile, the faint glow of Lyman-alpha blobs enormous clouds of hydrogen lit by embedded galaxies hint at how radiation pooled at filament junctions, creating temporary reservoirs of ionizing energy that could spill into neighboring voids. The cosmic web's ultimate role might defy simple labels. It wasn't just a passive stage for reionization. It was an active collaborator, shaping where and how light conquered the darkness. And as telescopes like the James Webb Space Telescope and next-generation radio arrays trace these ancient filaments in finer detail, they're uncovering a truth more profound than mere structure. They're revealing the invisible currents that guided the universe's transformation from shadow to light. One of the most electrifying and contentious discoveries in modern cosmology wasn't made by peering through a telescope, but by listening to the universe with what looks like a glorified coffee table. The EDGES experiment, a modest array of antennas in the Australian outback, made waves in 2018 when it claimed to detect a bizarre signal from the cosmic dawn, a dip in the 21-centimeter radio wave signature of primordial hydrogen that was twice as deep as theory predicted. This anomaly didn't just raise eyebrows, it threatened to upend our understanding of how light first interacted with matter in the infant universe. If confirmed, it could mean that hydrogen gas during the cosmic dawn was far colder than models allowed, or that some unknown force was amplifying the contrast between the cosmic microwave background and the gas. Either way, the implications for reionization would be profound. The 21-centimeter signal is supposed to be cosmology's Rosetta Stone, a direct transmission from the universe's darkest chapter. Neutral hydrogen atoms drifting through space occasionally flip the spins of their electrons, emitting faint radio waves at that precise wavelength. During the cosmic dawn, before stars flooded the cosmos with light, these signals should have been strong and clear, but as EDGES listened, it caught something peculiar, a trough in the signal around 78 MHz, corresponding to hydrogen's state roughly 180 million years after the Big Bang. The depth of that dip suggested hydrogen gas was chilling to temperatures around 4 Kelvin, nearly half what standard models predicted. For gas to get that cold that fast, it must have lost energy somehow, as if the universe had a hidden coolant system operating in the shadows. Theories to explain this anomaly range from the tantalizing to the borderline heretical. One camp argues for interactions with dark matter, specifically that certain hypothetical particles might have gently siphoned heat from the hydrogen through fleeting collisions. If true, this would mark the first direct evidence of dark matter influencing ordinary matter beyond gravity, rewriting particle physics overnight. Others propose more exotic ideas, like primordial black holes emitting radiation as they evaporated, or even cosmic strings defects in space-time left over from the Big Bang releasing energy in subtle bursts. Skeptics, however, point to mundane explanations: terrestrial interference, instrumental errors, or unaccounted for radio emissions from our own galaxy's outskirts muddling the signal. What makes this debate so pivotal is the signal's timing. The EDGES detection precedes reionization by hundreds of millions of years, meaning any physics affecting that early hydrogen would have set the stage for how easily later starlight could ionize it. Colder gas clumps more readily, potentially accelerating the formation of the first stars and galaxies. But if some unknown mechanism continued cooling gas during reionization itself, it could have created sheltered pockets where neutral hydrogen resisted ionization longer than expected, exactly the sort of anomalies we see in the Lyman-alpha forest and dwarf galaxy distributions. The edge's signal, if real, might be the missing link connecting these disparate puzzles, yet confirmation remains elusive. Follow-up experiments like Sarah's and Leda have failed to replicate the result, while upgraded versions of edges continue collecting data. The upcoming square-kilometer array could settle the debate, with sensitivity to map the 21-centimeter signal across the entire sky. Until then, the edge's anomaly lingers in limbo, a whisper from the cosmic dawn that could either reveal new laws of physics or fade into the static of history. Either way, it's a reminder that the universe's oldest light still holds surprises, and that sometimes the deepest mysteries are written in frequencies just beyond the edge of hearing. What if the universe didn't flip the lights on just once, but twice? The double reionization hypothesis is one of cosmology's most daring proposals, suggesting the cosmos endured not one but two separate waves of ionization, separated by an enigmatic lull where darkness temporarily reclaimed lost ground. At first glance, the idea seems to defy logic. How could the universe re-neutralize after stars and galaxies had already begun blazing? Yet a handful of quasar spectra reveal anomalies that refuse to fit neatly into the standard timeline, hinting at cosmic chaos we've yet to fully unravel. The evidence lies in the shadows cast by distant quasars. Normally, their light shows a predictable pattern. The deeper into reionization we look, the stronger the absorption from lingering neutral hydrogen. But a few outliers break this rule. Quasars like Euler's Joan 114+06 show Gunn-Peterson troughs that vanish unexpectedly early, as if their light passed through regions already ionized, only for later quasars to display deeper absorption again, like the universe had briefly regressed. It's as if we're reading a diary where someone wrote, "The lights are on," then scribbled it out to add, "Wait, no, they're off again." Proponents of double reionization point to population 3 stars as the key actors in this cosmic drama. These early behemoths, hundreds of times more massive than the Sun, could have ionized vast bubbles around themselves, but their explosive deaths might have triggered a collapse. When they detonated as pair instability supernova, their cataclysmic blasts could have swept away nearby gas, starving subsequent star formation and allowing neutral hydrogen to creep back into voids. The universe's first ionization attempt in this scenario was a false dawn, a brief flicker before the true reionization, driven by more stable galaxies and quasars, took hold millions of years later. Critics counter that the evidence remains circumstantial. Alternative explanations like patchy gas distributions or light contamination from foreground objects could mimic the spectral quirks without invoking a full cosmic reset. Even the timing is contentious. If a second wave occurred, it should have left scars in the cosmic microwave background's polarization, but current data shows no clear sign of such a reboot. Yet the hypothesis persists because it elegantly explains other puzzles, like why some regions of the Lyman-alpha forest appear over-ionized while others lag behind. The stakes are higher than they seem. If double reionization occurred, it would mean the universe's transformation wasn't a steady march but a stutter step, 2 steps forward, 1 step back. This would rewrite how we model early galaxy formation, suggesting some structures had to assemble twice, first in the brief initial ionization, then again after the collapse. It could even hint at undiscovered physics, like dark matter interactions that temporarily suppressed star formation or primordial magnetic fields that altered how radiation propagated. For now, the debate hinges on sharper data. Upcoming instruments like the 30-meter telescope aim to dissect quasar spectra with unprecedented precision, hunting for the chemical fingerprints of aborted ionization. Meanwhile, radio arrays probing the 21-centimeter signal could uncover fossilized bubbles from the hypothetical first wave, frozen in time like echoes of a cosmic false start. Until then, the double reionization hypothesis remains a thrilling possibility, a reminder that even the universe's brightest eras might have flickered before catching flame. Some of reionization's greatest architects might now be cosmic ghosts, black holes that vanished without a trace. Among the most perplexing absences in modern astronomy are intermediate mass black holes, those elusive objects bridging the gap between stellar remnants and supermassive giants. Ranging from hundreds to hundreds of thousands of solar masses, they should be everywhere, yet we've found only a handful. Their scarcity could hold the key to one of reionization's deepest mysteries. What if these missing behemoths were once prolific ionizers, flooding the early universe with radiation before disappearing into the cosmic shadows? Consider the timeline. In the chaotic nursery of the early cosmos, dense star clusters and direct collapse gas clouds could have birthed intermediate black holes by the thousands. Unlike their supermassive cousins, which took eons to grow, these mid-sized predators might have formed quickly, feasting on the pristine gas around them. Their accretion disks would have blazed with intense ultraviolet and X-ray radiation, precisely the energy needed to strip electrons from hydrogen on staggering scales. Simulations show just one such black hole, a mere 10,000 solar masses, could ionize a bubble spanning thousands of light years, creating oases of light in the cosmic dark long before galaxies grew powerful enough to contribute. Yet if they were so influential, where did they all go? One possibility is grimly poetic. They consumed themselves out of existence. Early black holes forming in gas-rich environments might have gorged so voraciously that their own radiation heated and expelled nearby fuel, starving themselves into dormancy. Others could have been flung into the void by gravitational slingshots during galactic collisions, doomed to wander intergalactic space as invisible nomads. A few might still lurk in modern galaxies, camouflaged within globular clusters or disguised as unusually bright X-ray binaries, cosmic sleeper agents waiting to be unmasked. The alternative is even more intriguing. What if these black holes didn't vanish but grew up? The same feasting that made them ionizing powerhouses could have fueled runaway growth, allowing some to balloon into the supermassive black holes we see today. This would solve another puzzle: how quasars existed so early in the universe. Their seeds might not have been modest stellar remnants, but pre-grown intermediate monsters from the reionization era's wild youth. The catch: this scenario predicts a wealth of mid-sized black holes in the modern universe that we simply haven't found. Unless our detection methods are missing an entire population, their absence suggests a different fate. Perhaps the answer lies in their birthplaces. Many early intermediate black holes could have formed in small proto-galaxies that later merged or were cannibalized by larger neighbors. Their signatures would dissolve into the noise of supermassive black hole mergers, leaving no trace beyond skewed mass distributions in galactic cores. Others might have been shredded by tidal forces in dense environments, their remains scattered like ashes across the cosmic wind. The James Webb Space Telescope could settle the debate by hunting for telltale X-ray glows from early black holes just below supermassive size, evidence they once ruled the cosmos before fading into obscurity. Their legacy, however, would endure in the ionization patterns they left behind. If these missing black holes were indeed reionization's shadow workforce, their bubbles of influence might explain why some regions of the early universe appear over-ionized compared to others. Like footprints in wet cement, their brief but brilliant lives could have set the stage for the universe we see today, not through slow, steady progress, but in explosive fits and starts written in light and erased by time. Until we find them, their story remains half-told, a cosmic whodunit where the suspects have vanished, leaving only echoes of their transformative power. Among the rarest objects in the modern universe are galaxies that shouldn't exist, at least not by the rules we thought governed cosmic evolution. Dubbed Lyman continuum leakers, these enigmatic galaxies defy all expectations by spewing torrents of ionizing radiation into space, the kind of extreme ultraviolet light that should be bottled up tight inside them. They're the cosmic equivalent of a flashlight with no casing, somehow shining ultraviolet rays directly through walls that stop every other galaxy's light. What makes them even more fascinating is that they might be the closest thing we have to time machines, offering a glimpse of how galaxies behaved during the reionization era when the universe was young and raw. The mystery begins with a simple fact. Today's galaxies are terrible at leaking ionizing photons. Modern star-forming galaxies wrap their ultraviolet radiation in thick cloaks of gas and dust, absorbing or scattering nearly every Lyman continuum photon before it can escape. It's why astronomers typically observe these energies only in the sparse intergalactic medium or around quasar sources powerful enough to punch through galactic barriers. So when telescopes like Hubble and later the James Webb Space Telescope spotted ordinary-looking galaxies pouring out ionizing radiation like sieves, it upended decades of assumptions. Somehow, these galaxies, often compact, turbulent, and low in heavy elements, are doing what their modern counterparts cannot, flooding the cosmos with photons capable of stripping electrons from atoms. One leading theory suggests these leakers are cosmic throwbacks, relics of an earlier era preserved by chance. Their small sizes and chaotic structures resemble computer simulations of reionization era galaxies, where UV radiation escaped easily through channels carved by supernova or where sparse dust allowed photons to slip away unimpeded. The most famous example, Galaxy Joan 509-2416, leaks an astonishing 60% of its ionizing radiation, a figure that would have made it a heavyweight contributor during reionization. Its chemical makeup adds to the intrigue. Remarkably low in metals, it mirrors the conditions of galaxies born just hundreds of millions of years after the Big Bang. If these objects were more common in the past, they could have been the unsung heroes of reionization, their collective light overwhelming the cosmic hydrogen fog. Yet alternative explanations lurk in the shadows. Some leakers don't fit the primordial mold, they're metal-rich or show signs of recent collisions, suggesting their radiation escapes through different mechanisms. A violent merger might have torn open gas clouds, creating temporary gaps for photons to flood out. Others could harbor hidden Aegean activity, their central black holes pumping out just enough X-rays to mimic the Lyman continuum signature. The most puzzling cases show no obvious structural differences from non-leaking galaxies, raising the unsettling possibility that subtle factors, like magnetic field orientations or the specific trajectories of stellar winds, might determine whether a galaxy becomes a cosmic sieve or a sealed vault. This isn't just academic curiosity. If leakers are true analogues of reionization-era galaxies, studying them could reveal why some early galaxies were so efficient at ionizing their surroundings. Their stellar populations might skew toward massive, short-lived stars, or their gas distributions could naturally favor escape routes modern galaxies lack. Alternatively, if they're outliers with unique physics, their existence hints at processes we've overlooked in our reionization models. Perhaps rare evolutionary stages all galaxies pass through, or environmental factors that temporarily unlock their ionizing potential. The key to unraveling their secrets lies in hunting more of them. Current samples number in the dozens, a statistical drop in the ocean compared to the billions of galaxies in the observable universe. Upcoming missions like the Nancy Grace Roman Space Telescope aim to change that, scanning vast swaths of sky for these ultraviolet rebels. Each new discovery adds a piece to the puzzle, helping us distinguish between cosmic accidents and echoes of the past. One thing's certain, in a universe that's supposed to play by set rules, Lyman continuum leakers are the thrilling exception, whether they're whispers from the reionization frontlines or rogue players rewriting the galactic rulebook. Every revolution must end, even the cosmic one that lit up the universe. The grand finale of reionization poses a puzzle just as profound as its beginning. Why did this epoch of transformation eventually grind to a halt? After hundreds of millions of years of relentless ionization, the universe didn't just flicker out, it reached a state where nearly every hydrogen atom had been stripped of its electron. But what flipped the switch from chaos to equilibrium? The answer might rewrite not just the history of our cosmos, but the fundamental rules governing how light and matter interact on the grandest scales. Two competing narratives dominate the debate. The first suggests reionization ended with a whimper, not because the universe ran out of ionizing sources, but because it simply ran out of targets. Picture a wildfire burning through a vast forest. Once every tree has been reduced to ash, the flames have nothing left to consume. In this scenario, galaxies and quasars continued pumping out ultraviolet radiation, but with most hydrogen already ionized, their photons traveled vast distances without encountering neutral atoms to split apart. The irony is stark. The very success of reionization made its continuation impossible, leaving later photons to wander the cosmos like bullets fired into an empty battlefield. The alternative theory flips this logic on its head. Perhaps reionization's conclusion wasn't passive at all, but an active balancing act between creation and destruction. Ionized gas doesn't just stay free forever. Electrons and protons can recombine, especially in denser regions like galactic halos or filamentary structures. Some models propose that the universe reached a dynamic equilibrium, where the rate of new ionization matched the rate of recombination. This delicate stalemate would have been maintained by a cosmic seesaw. As ionizing sources grew more numerous, their radiation suppressed star formation in smaller galaxies, which in turn reduced the supply of new ionizing photons. The universe, in effect, became its own thermostat, self-regulating its ionization state until it stabilized into the transparent cosmos we know today. Observational clues add layers of complexity. Deep surveys of quasars at the tail end of reionization show a curious pattern, while most display the expected lack of hydrogen absorption. A few still exhibit faint Gunn-Peterson troughs, as if patches of neutrality lingered like stubborn stains. This contradicts the clean, mission-accomplished narrative, hinting that reionization's endgame was messier than simulations predict. Even stranger, the cosmic microwave background's polarization data suggests the process didn't wind down smoothly, but in fits and starts, with some regions declaring victory long before others. The most tantalizing wildcard, the role of temperature. Ionized gas is hot gas, and hot gas resists recombination. But as the universe expanded, this gas cooled, potentially allowing electrons and protons to reunite in shadowy pockets. If cooling outpaced ionization in certain regions, reionization might have locally reversed before radiation from neighboring galaxies rebooted the process. This stop-and-start scenario could explain why some ancient quasar spectra appear sandwiched between ionized and neutral layers, like geological strata recording cosmic climate shifts. The ultimate resolution might lie beyond traditional astrophysics. Some theorists speculate that dark matter's gravitational influence subtly altered the timeline, with dense halos acting as recombination hotspots that siphoned off ionizing photons. Others explore exotic ideas like decaying dark matter particles releasing a final burst of energy to mop up remaining neutral hydrogen. The truth could be a tapestry woven from all these threads, a story where the universe's lighting was never controlled by a single switch, but by countless hands working in imperfect concert across the eons. What's certain is that reionization's finale wasn't an ending, but a transformation. The transparent universe it birthed became the stage for everything that followed: galaxies colliding, stars igniting, and eventually, life awakening to ponder the very forces that made its existence possible. And somewhere in the fading echoes of that last neutral hydrogen atom's dissolution lies a lesson. Even the universe's most epic transformations don't conclude with a bang, but with the quiet satisfaction of a puzzle finally solved. From the enigmatic trigger that ignited reionization to the lingering shadows of neutral hydrogen defying the cosmic tide, these 25 mysteries aren't isolated riddles. They're threads in a tapestry we've only begun to unravel. Consider how population, 3 stars vanishing act ties to the missing energy budget, or how the Gunn-Peterson trough's ghostly imprints intersect with the Lyman-alpha forest's chaotic patterns. Even the cosmic web's invisible architecture plays its part, shaping where and when light could pierce the darkness. Together, they reveal a universe far messier, far more improvisational than our tidy models predicted, a place where black holes may have flickered in and out of influence, where galaxies formed in fits and starts, and where dark matter might have whispered its presence through subtle nudges we're just learning to detect. The beauty of these unsolved puzzles is their interconnectedness. The escape fraction problem isn't just about galaxies. It's a key to understanding why some regions ionized faster than others. The Edge's anomaly doesn't merely hint at cold hydrogen. It could rewrite how we map the entire timeline from cosmic dawn to reionization's finale, and those dwarf galaxies stubbornly surviving against the odds. They're not cosmic accidents, but witnesses to reionization's uneven reach, holding clues about the environments where light first triumphed. Every mystery solved doesn't just fill a gap, it sends ripples through our understanding of the whole era. Thankfully, we're not left guessing forever. The James Webb Space Telescope is already peeling back layers of the early universe with infrared precision, spotting galaxies so ancient they blur the line between cosmic dawn and reionization. Soon, the square-kilometer array will tune into the 21-centimeter whispers of primordial hydrogen, tracing ionization spread across billions of light years. Meanwhile, next-generation telescopes like the Extremely Large Telescope and the Nancy Grace Roman Space Telescope promise to dissect quasar spectra and dwarf galaxy chemistry with unprecedented clarity. These missions don't just aim to answer questions, they'll redefine what we think to ask. So as we stand at the edge of these discoveries, remember, the story of reionization isn't some distant cosmic history. It's the origin of everything we see, the galaxies, the stars, even the atoms in our bodies. And with each passing year, as telescopes grow sharper and models more refined, we're piecing together how darkness gave way to light. The greatest lesson these 25 mysteries teach us isn't about the past, but the future. That curiosity is our compass, and the universe always has more secrets to share. Where the next breakthrough will come from, no one knows, but that's the thrill of the hunt. Stay tuned, stay wondering, and above all, keep looking up. The Cosmic Dawn's final chapters are still being written, and you've got a front